Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
Wiggles. For example, waveforms, like the sound of music. Question: what does it take to reproduce that original sound? Or signals, like Morse code against a background of noise. Question: what does it take to hear the message more clearly? Or charts, like an electrocardiogram. Question: how can we tell whether this patient is at risk from heart attack? Or traces, like seismic echoes from deep within the earth. Question: shall we find oil or not? Or graphs, like the price of a stock on the stock market. Question: is it cyclic? And if it is cyclic, where are we on the cycle today? To buy or not to buy? These are the questions that we shall find the means to answer in these two videotapes. Oh, and all without a single equation.
We start with the most basic of wiggles, the snake-like waveform that we call a sinusoid.
It might represent the ups and downs of a bumpy road, in which case the horizontal axis is distance.
Or it might represent the variation of temperature with the seasons, in which case the horizontal axis is time.
In fact, we shall speak as though our waveforms are always waveforms in time, but everything we say is equally valid for waveforms in space.
Okay, now, how to generate a sinusoid? A wheel on a shaft with a colored peg near the rim. Now we turn the wheel, round it goes. We also need to see the wheel sideways. Again, we turn. From the front, we have circular motion. Uniform, regular, steady. From the side, we have sinusoidal motion. Slow at top and bottom, fast in the middle. And if we plot the motion as a function of time, we have our sinusoid. Let's call up positive and down negative. So there's the full picture. Sinusoidal motion, positive peaks, negative troughs, symmetrical above and below the axis.
Next, some terms. One revolution of the wheel draws one cycle of the sinusoid. The time taken for one cycle is one period. If we add a time scale, we see that in this case there is one cycle in 1 second. The number of cycles in 1 second is called the frequency and is measured in hertz.
The frequency, then, is a measure of the speed of the wheel. A sinusoid of 1 hertz. A sinusoid of 2 hertz. And a sinusoid of 4 hertz.
A range of 2 to 1 in frequency is called an octave. From this to this. 4 times the frequency is 2 octaves. 1 octave from here to here, 1 more from here to here.
Just as in music. 1 octave from this to this, 1 more to this. up or down.
Okay, so much for frequency. Now, phase.
Thus far, we've started the wheel with the peg at the top, and so the sinusoid also starts at the top. At 0 time, there's a peak. But suppose we choose to start the wheel at some other position. In effect, we move the wheel through a certain angle before we start. Then, of course, we also move the sinusoid along the time axis.
We call the starting angle, the angle at 0 time, the phase angle. Its effect is to shift the sinusoid in time. If we advance the wheel before we start, we call it a phase lead. It moves the sinusoid earlier. If we retard the wheel before we start, we have a phase lag, and the sinusoid comes later.
If, for example, the phase angle is 60 degrees, which is 1/6 of a full revolution, then the time shift is 1/6 of a period.
It is the 0 phase condition that we shall use as our standard. The sinusoid corresponding to 0 phase has a peak at 0 time. We call it a cosine wave. This will be our standard basic waveform in all the following material.
If, relative to this waveform, we impose a phase lag of 90 degrees, the waveform is delayed by a quarter period. It now has its 0 value at 0 time, 0 and rising, the sine wave.
Going on round to 180 degrees, lead or lag, the waveform is now upside down. The original waveform inverted.
Round to 270 degrees, and the waveform again has its 0 value at 0 time, but now falling. In fact, it is the 90-degree wave, the sine wave, upside down.
Indeed, it is always true that changing the phase angle by 180 degrees inverts the wave.
Finally, if we go on round to 360 degrees, we cannot distinguish this condition from the original 0 condition. Shifting a sinusoid by 1 or more full cycles yields no change.
Because of this, the sinusoid does not actually have to start at 0 time. We can assume it has been running forever, and that it goes on forever. We just select the time origin, at a peak for a cosine wave, and let times before that be negative.
So, there is our basic waveform, the cosine wave, going on forever in both directions. 0 phase with a peak at 0 time and symmetrical about 0 time.
Good. One thing more, amplitude, the vertical measure of the sinusoid.
A sinusoid is completely specified by these 3 measures: its amplitude, its period, or reciprocal the frequency, and its phase.
Okay, let's take this cosine wave as our building block and see what magic we can make. First, 2 identical sinusoids. And let's add them together.
By add,
By add, I mean add this value on one wave to the corresponding value on the other. That's the value at the same time. And plot the answer as a new waveform. The result is another sinusoid of the same frequency, but double the amplitude. Reinforcement.
double the amplitude because you set them both in phase. But if you'd taken them appreciably out of phase, less amplitude. And more out of phase, less amplitude still. Until if they are in antiphase, 180 degrees out of phase, result is zero. Cancellation.
So we can say the result of adding two sinusoids of the same frequency is another sinusoid of the same frequency, but whose amplitude depends on the relative phase.
Fine. Now, let's add two sinusoids of different frequency. In phase at zero time, so at that time, reinforcement. At other times, cancellation. And the final result? A new sinusoid of intermediate frequency, falling and rising in amplitude.
The phenomenon of beats. Here, just listen. A sinusoid and another of slightly different frequency. Together, there. Hear the beats?
Here's a very important case of that. One sinusoid, which we shall call the fundamental, then another sinusoid of double the frequency, which we shall call the second harmonic. And the sum waveform, quite distinctive. But if we change the phase of the second harmonic, a different sum waveform. Clearly, we can obtain a wide variety of sum waveforms from the same component sinusoids merely by changing the relative phase between them.
Just show me those sum waveforms all together. Yes, I thought so. In each case, the sum waveform repeats with the period of the fundamental.
Right. Now, let's take the same fundamental, but add the third harmonic. Again, a whole variety of sum waveforms depending on the relative phase.
Yes, but again, the sum waveform repeats with the period of the fundamental.
The variety of the sum waveforms we get by adding a fundamental and its harmonics prepares us for a very important conclusion. Any repetitive waveform can be synthesized by adding sinusoids.
Even a square wave, or a sawtooth wave, or a regular heartbeat.
And the frequencies of the sinusoids to be added are always 1, 2, 3, 4, 5 times the frequency of the basic repetition, the fundamental and its second, third, fourth, fifth harmonics.
I still marvel at that. It's certainly not self-evident.
No, it's not. Fourier, who discovered it, had difficulty convincing the scientists of the day that it was true. Perhaps that was because he was an engineer.
Fourier's concept explains, among other things, the different tone of musical instruments. A flute, almost a pure sinusoid. A thin sound. Then if we play the same notes, the same fundamentals, but with the right harmonics, we have an accordion.
Or an organ. Different proportions of the harmonics give a different sound.
But back to work. The diagram that shows the amplitude of the sinusoidal components as a function of frequency is called the amplitude spectrum. The fundamental, the second harmonic, and so on.
And the diagram that shows the phase of the sinusoidal components is called the phase spectrum. The phase angle of the fundamental and each harmonic.
Then our previous conclusion that any repetitive waveform can be synthesized by adding sinusoids can be restated as any repetitive waveform is completely specified by its amplitude and phase spectra for the fundamental and the harmonics.
Good. Let's explore that with just 4 components of equal amplitude, a flat amplitude spectrum. And for now, let's set all the phase angles to 0, 0 phase. The fundamental is this sinusoid. The second harmonic, the third harmonic, and the fourth.
Look, I like specific numbers. Can we make the fundamental 10 hertz and then 20, 30, 40?
Sure, just for illustration. Then the fundamental at 10 hertz means that this period is 1/10 of a second, that the second harmonic has 2 cycles in 1/10 of a second, the third 3, and so on.
And the 0 phase spectrum says that all the sinusoids are cosine waves with a peak at 0 time.
Then we do the addition and get that.
Of course, it comes out large because the addition is in phase at 0 time. Can we scale it down?
Sure. Let's divide by the sum of the amplitudes, in this case by 4. We say we're normalizing the sum.
Yes, that's better. We should always do that when it's the shape of the waveform we're interested in, rather than its amplitude.
Okay, now, here's an interesting thing. Let's take the fundamental and remove it. The normalized sum is then like so.
And the interesting thing
Is that although the fundamental is missing, the sum waveform still repeats with the period of the fundamental.
So it does. That must be because the frequency of the fundamental is still defined by the frequency of the harmonics.
Right. The highest common factor of 20, 30, and 40 is 10. The implied frequency of the fundamental is the highest common factor of the components.
Let's check by taking out the 30 hertz also. Then the highest common factor is 20 hertz. And the sum repeats not every 10th of a second, but every 20th of a second. So it does. We can say the frequency of repetition is the highest common factor of the frequencies of the components.
All right. So looking at the amplitude spectrum, 10, 20, 30, 40 hertz, we know that the corresponding waveform must repeat,
Every 1/10 of a second.
and the waveform corresponding to components every 5 hertz must repeat,
Every 1/5 of a second.
and the waveform corresponding to components every 2 hertz must repeat.
Every half a second.
And if we put components infinitesimally close, so that the spectrum ceases to be a line spectrum and becomes a continuous spectrum,
The corresponding waveform never repeats.
what? Never?
No, never. Line spectra represent repetitive waveforms. Continuous spectra represent transient waveforms.
For us, the problem with continuous spectra is that an infinite number of components takes forever to draw. But in practice, there is always some period after which the waveform may be allowed to repeat. Then we can go back to a line spectrum, to a finite number of components, and draw them. Let's insist on half a second without repetition. Then we'll have components every 2 hertz from 10 to 40 hertz. Equal amplitudes, and for the moment, 0 phase. The sinusoidal components, and their sum.
Stretch them out a bit.
Yes, there's no point in showing more than one period of the fundamental. Everything just repeats beyond that.
Okay, let me have a go. I'll take a wider band of frequencies, say 10 to 80 hertz. A greater bandwidth, as we say. The components and their sum.
Notice that the sum waveform now looks more like a pulse, quite a sharp pulse. Before, for 10 to 40 hertz, 2 octaves, it was less sharp. Now, with the greater bandwidth of 10 to 80 hertz, 3 octaves, it is sharp again. And if we go in the other direction to less bandwidth, say 20 to 40 hertz, 1 octave, it is still a pulse, but certainly not a sharp one. We say it's ringy.
Not surprising. In the limit, when the bandwidth is very small, the sum waveform must be a sinusoid, which goes on ringing forever. As the bandwidth increases, a pulse, but ringy. More bandwidth, sharper pulses. At the other limit, infinite bandwidth, from 0 frequency to infinity, a very sharp pulse indeed, a spike.
So we have an important conclusion. Short pulses must have large bandwidth.
Right. That's critical in any application where we have to time the arrival of a pulse. Precise timing needs pulses of large bandwidth. It's easy to time the arrival of a spike, or even this. But to time this is imprecise. And to time this is impossible.
Okay, now let's just look at one of these pulses more carefully, say 10 to 40 hertz. Writing on the pulse, we can see 10 hertz and 40 hertz, the edge frequencies of the spectrum. To see why, let's go back to the Fourier components which make up the pulse. There they are, and their sum. At the time origin, the 0 phase spectrum requires that they are all in phase at a peak. Away from the time origin, where the components are out of phase, This frequency is smoothly canceled by the frequencies each side of it, and it cannot be seen in the sum waveform. But the cancellation does need the frequencies on both sides. So when we look at the edge frequencies, their cancellation is incomplete. That's why we see them out here, forming these side lobes to the pulse.
That suggests that if we were to reduce the amplitude of the components near the edges of the spectrum, we would get less side lobes, a cleaner pulse.
Right. From the rectangular spectrum, with its sharp corners, we get this pulse. From the same spectrum with rounded corners, we get a cleaner pulse.
So we can say sharp shoulders on the amplitude spectrum mean large side lobes on the pulse.
Indeed, if we want a short pulse, standing out cleanly from the background, then the amplitude spectrum needs to be smoothly peaked.
A short, sharp pulse means a broad, smooth spectrum.
All right, now all that was for zero phase. Symmetrical pulses with their maximum at zero time. Let's keep that peaked amplitude spectrum and its corresponding zero phase pulse. On the phase spectrum, thus, zero phase. Now what happens if we change the phase of all components by the same angle? Let's try a lag of, say, 45 degrees on all components, and one of 90 degrees, and one of 135 degrees, and one of 180 degrees. The 180 degree phase is easy. That just inverts each component, and so inverts their sum. The 90 degrees phase lag, we remember, changes each cosine wave to a sine wave, with a zero crossing at the time origin. So the sum is also skew symmetric.
I call that a 90-degree shape.
Okay. And of course, the intermediate 45-degree shape is intermediate, and the intermediate 135-degree shape, intermediate again.
So if we concentrate on a particular part of the waveform, say this peak, we see that it does lag increasingly.
Yes, but that peak also gets smaller. A particular part of the waveform lags, but the pulse as a whole, the envelope, does not. The envelope is still centered about zero time.
So far, we're only halfway round the phase clock. Let's go on round. 180 degrees lag is the same as 180 degrees lead, the phase clock, and the corresponding pulses. Because these two angles differ by 180 degrees, their pulses are inverted versions of each other. Similarly, because these two angles differ by 180 degrees round the phase clock, these pulses are inverted versions of one another.
We still see the effect of increasing lag on a particular peak, but we still see that there is no lag on the pulse as a whole.
To get lag on the pulse as a whole, we need a linear phase spectrum. Let's just consider two frequencies an octave apart. Two frequencies that would have been aligned like this for a zero phase spectrum. Now with this phase spectrum, double the frequency, double the phase shift, the first frequency is lagged by, let's say, a quarter cycle. So the second frequency, double the first, is lagged by a half cycle. The same time shift. So the sinusoids are still in phase, but later.
Neat, isn't it? For a zero phase spectrum, the components are in phase. If we rotate the phase spectrum about the origin, the components are still in phase, but delayed.
So a linear phase spectrum, projecting back through the origin, preserves the zero phase form, but imposes a delay proportional to its slope.
Now, what if the linear phase spectrum does not project back through the origin? Here, for example, it projects back to a 90-degree lead at zero frequency. Well, we already know what a constant 90-degree lead does. It gives us this 90-degree shape. Let's store that. Its phase spectrum also projects back to a 90-degree lead. Now, we rotate the phase spectrum about that point, just as we did before, and the pulse is delayed. The same shape, the same envelope, but delayed.
So for a given amplitude spectrum, the phase spectrum has this effect. The intercept on the phase axis determines the shape. The slope determines the delay.
Okay, now what about a curved phase spectrum? Well, we can still get some idea what must happen. First, we look at the amplitude spectrum. The frequencies near the peak must be contributing the most. Over those frequencies, the phase spectrum is approximately linear, with a certain slope and a certain intercept. The intercept, we know, would give us this pulse shape. The slope, we know, would impose this delay. So that is the basis of the pulse. Then at high frequencies, the slope is less, so that the delay is less. The final pulse must be richer in high frequencies toward the front, while at low frequencies, a steeper slope, more delay, richer in low frequencies in the tail.
So we begin to get some feeling for this one-to-one relationship between a waveform and its two spectra. The amplitude spectrum, with its easy message about the frequencies present, and the phase spectrum. I used to think the message in the phase spectrum was too subtle for me, but it isn't. Not this way.
There's one more phase spectrum we must mention.
Yes. Minimum phase.
Given an amplitude spectrum, there are an infinity of phase spectra, and so an infinity of waveforms. But two phase spectra are of particular importance. One is zero phase, which we know gives this symmetrical pulse. Actually, the shortest pulse obtainable with that amplitude spectrum. The other is minimum phase, which is the phase spectrum characteristic of many natural waveforms.
Natural waveforms?
Yes, this isn't natural, is it? When we were drawing cosine waves, which go on forever, we could put the time zero on any peak we liked, and negative times were no problem. But when our waveform is the sound from a hand clap, I decide the time zero, and before that there must be nothing. A minimum phase pulse satisfies this requirement. It's one-sided.
And another important feature. It concentrates the pulse energy as close to the front as the amplitude spectrum allows. It's front-loaded.
Natural. And one more important property of minimum phase. The phase spectrum can be calculated uniquely from the amplitude spectrum.
No calculations, thank you.
Well, you can do it graphically, too. That's in the manual. But this property of minimum phase is a great simplification, because it means that a minimum phase waveform, a natural event, is completely specified by its amplitude spectrum alone.
Yes, that is a simplification. Still intriguing to me, though, that all those sinusoids in the amplitude spectrum could add before zero time to give nothing.
Yes, it is a very particular phase relation. But if it's the intriguing you're after, tell me this. How did Fourier know when I would clap my hands?
Spooky.
A summary so far. Any sort of physical variation of anything with anything can be regarded as a waveform. If the waveform is repetitive, it can be taken as the sum of sinusoidal components, Fourier components, harmonics of the fundamental repetition. If the waveform is transient, we regard it as repetitive over a very long period, so that the fundamental frequency is low and the harmonics closely spaced. In either case, the relative proportions of the sinusoidal components are shown by the amplitude spectrum, and their relative shifts along the axis by the phase spectrum. If the waveform is in the time domain, it defines the spectra in the frequency domain. The waveform defines the two spectra define the waveform, total equivalence. Indeed, we may look at a waveform with a little practice and estimate the two spectra, or we may look at a pair of spectra and estimate the waveform. This powerful principle is the Fourier transform. There's more on it, of course, in the manual. Guidelines, examples, and a little more on phase, on the convenience of zero phase, on the naturalness of minimum phase, and the unnaturalness of anything else. But for the moment, let's go on to operators.
If a waveform is input to a system, the system is said to operate on the input waveform to produce an output waveform.
So that the same music heard on a cheap radio or on an expensive radio sounds different.
The first question we must ask is the system linear?
Linear here has its usual meaning of a straight line relationship. In this case, between input and output. For inputs both positive and negative. Double the input, double the output. Linear.
Well, let's say that's near enough for present purposes. Now, what does such a system do to a sinusoid?
For a linear system, pure sinusoid in, pure sinusoid out, at the same frequency.
Right. Contrast that with a system that is linear only up to some limit. The output waveform has its peaks and troughs clipped off. It is no longer a sinusoid. It is still repetitive and is therefore the sum of the fundamental and many harmonics. A nonlinear system, therefore, generates harmonics.
One more example. A so-called rectifying system, which turns every negative value into a corresponding positive value. The output is now all harmonics. There is nothing left at the original frequency.
A waveform passing through any nonlinear system, such as this, or this, is therefore distorted. The effect is called harmonic distortion, and the measure of the distortion is the amount of harmonics added.
Distortion? Ugh!
Yes, ugh indeed. Linear systems are much simpler. Further, if two linear systems are cascaded, then for most common operations, the output is the same if A comes first or if B comes first. The order is immaterial, and this is an important feature of linear systems.
From here on, then, we shall avoid any system showing non-linearity, looking particularly for any kind of stops limiting the motion, or any lost motion, or stickiness, or any kind of one-way valve allowing positive flow but not negative, or any mathematical manipulation destroying the simple proportionality between input and output. We shall concentrate on linear systems, for which we have agreed that an input sinusoid yields an output sinusoid of the same frequency.
That does not mean that output and input are necessarily of the same phase, nor of the same amplitude. The system could attenuate this frequency or amplify it.
Yes, and whether the system attenuates or amplifies can depend on the actual frequency applied. Let's consider a weight hanging on a spring. For small displacements, this is a linear system, but with an action that depends on frequency. Here, this is brute force work, your sort of work. You raise and lower the top of the spring, and I'll graph what happens to the weight. Yes, that's right. At very low frequencies first. The weight follows your hand exactly, up and down together. The output is equal to the input, and there is zero phase angle between them. All right, the output is equal to the input, and the phase angle between them is zero. Now do it a bit faster, keeping the same input displacement. That's it. The weight is now moving more than your hand. We have struck a resonance, and the weight is lagging. There is a 90-degree phase lag. Output more than input, amplification. And phase, lagging 90 degrees. All right, now faster still, keeping the same displacement. The weight is now moving very little. Weights don't like high frequencies. And what movement there is exactly out of phase. Output much less than input, attenuation. And phase, lagging 180 degrees.
These two curves are very important. We call them the system response curves. The ratio of output amplitude to input amplitude is the amplitude frequency response.
I just call it the amplitude response.
And the phase angle between output and input is the phase frequency response.
I just call it the phase response.
As a waveform, then, is completely specified by its amplitude spectrum and its phase spectrum, so a linear system is completely specified by its amplitude response and its phase response.
Important indeed, for it leads to a solution to the problem we posed just now. Knowing the input waveform, and therefore its input spectra, amplitude and phase, and having the system responses, amplitude and phase, how can we deduce the output spectra, and hence the output waveform?
We start with the input waveform, which is one whose spectra we already know, 20 to 40 hertz, zero phase. So we replace the waveform by these equivalent spectra, 20 to 40 hertz, rectangular amplitude spectrum, zero phase spectrum. Now, for a first example, let's pass that waveform through a system whose amplitude response is unity, output equal to input, from 10 to 80 hertz, and whose phase response is linear, lagging. Then, the 20 hertz component in the input waveform enters the system where it is multiplied by the ratio of output amplitude to input amplitude, which is 1. The output is the same as the input. All other frequencies in the input, up to 40 hertz, are similarly multiplied by 1 in the system. They pass through unchanged.
So the amplitude spectrum of the input, multiplied by the amplitude response of the system, yields the amplitude spectrum of the output.
And now, phase. The 20 hertz component in the input waveform has a phase of 0. The system imposes a certain phase lag, so that the output has that phase lag also. Similarly, over all other frequencies in the input.
So that we can say the phase spectrum of the input plus the phase response of the system yields the phase spectrum of the output.
Yes. To get the amplitude spectrum of the output, we multiply the amplitude spectrum of the input at each frequency by the amplitude response of the system. To get the phase spectrum of the output, we add the phase spectrum of the input at each frequency to the phase response of the system.
In short, we multiply the amplitude curves and add the phase curves.
Having done that, we have an output amplitude spectrum and an output phase spectrum, which together define an output waveform.
Now, if we compare that with the original input waveform, we can see what the system has done in the time domain.
Because the amplitude response of the system was flat, beyond the limits of the input, the sinusoidal components in the output are the same. Because the phase response of the system was linear, again beyond the limits of the input, the sinusoidal components are still in phase at one point, but delayed. The output waveform is identical to the input waveform, but delayed in time.
So we have the criterion that a system should pass a waveform without change. The amplitude response must be flat, at least over the bandwidth of the input. And the phase response must be a straight line, projecting back to 0 degrees, again at least over the bandwidth of the input. This, then, is the criterion of perfect fidelity.
Every hi-fi salesman knows the first part, that the amplitude response of the hi-fi must be flat over the bandwidth of the music. They all take that to fanatical degrees. But next time you're buying a piece of hi-fi equipment, ask the salesman this: is the phase response a straight line, and does it project back through 0 degrees at 0 frequency?
Let's do another one.
Okay, an input waveform. One-sided this time, a natural event of some sort. The corresponding amplitude and phase spectra, again, natural. Then let's take a system which has a flat amplitude response up to some cutoff frequency, and then 0 response. And let's take 0 phase for the phase. Then, multiplying the amplitude curves, we have the amplitude spectrum of the output, an odd-looking spectrum with one sharp corner. And adding the phase curves, we have the phase spectrum.
That's interesting. If the input phase spectrum was minimum phase, then the output phase spectrum, although it has the same form, is not minimum phase, because the amplitude spectrum has been changed.
That's right. Because each amplitude spectrum uniquely defines its own particular minimum phase spectrum.
Okay, let's consider the output waveform then. I'm going to guess it rings at that corner frequency, and that it is obviously not minimum phase. Good guess, huh? Put the input waveform up again. Yes. Narrowing the amplitude spectrum makes the pulse longer, and imposing a sharp corner makes it ring. And the non-minimum phase shows before 0 time, probably in the general delay of the pulse envelope too.
Okay, now let's try one more input waveform, the spike. We remember that its amplitude spectrum is flat all the way from 0 frequency to infinity. It contains all frequencies equally. We call it white, by analogy with white light. Then, since the spike is symmetrical about 0 time, we know that its phase spectrum must be 0 phase.
Okay, let me choose the system responses this time. A nice, smooth amplitude response. And for that amplitude response, its very own minimum phase response.
Okay, then multiplying and adding as usual, we must have an amplitude spectrum the same as the amplitude response of the system, and a phase spectrum the same as the phase response of the system.
So by using a neutral input, like a spike, containing all frequencies equally and with 0 phase, we get output spectra which are identical to the responses of the system. These output spectra, therefore, measure the responses of the system.
Okay, one more important step. The time waveform we get from those spectra, therefore, totally characterizes the system. We call it the impulse response of the system. For a spike at the input, we get the impulse response at the output.
Previously, we agreed that a linear system is completely specified by its amplitude response and its phase response. Now we can also say a linear system is completely specified by its impulse response.
Those system responses you chose, they look familiar.
I meant them to be. They're from the weight hanging on a spring.
Okay, let's see if it checks. To inject a spike into this system, I must very quickly raise the top end of the spring and bring it back again. Ready?
Ready.
As fast as the eye can see. Go. There. Graph the movement of the weight.
Got it. That's the output when the spike is the input. Do it again to make sure. Yes, that's it. The impulse response of a weight hanging on a spring.
So, just as there are 2 ways of characterizing a waveform, as the waveform itself in the time domain, or as the amplitude and phase spectra in the frequency domain, so there are 2 ways of characterizing a linear system. We may do it in the time domain by injecting a spike and by measuring the impulse response. Or we may do it in the frequency domain by injecting sinusoids under steady conditions. Then we measure at each of many frequencies the ratio of amplitudes between output and input, the amplitude response, and the phase angle between output and input, the phase response. The two responses in the frequency domain are totally equivalent to the impulse response in the time domain.
It follows then that the impulse response has an amplitude spectrum of the same form as the amplitude response, and the phase spectrum of the same form as the phase response.
Must not confuse them, though. The waveform has spectra. The system has responses.
All right. Now, let's go back to our fundamental problem. How to know what the output is and see how it helps us to know the impulse response of the system.
Here, let me do this bit. I just love the simplicity of it.
Okay, off you go.
At the input, a spike. For graphic purposes, I'll just flesh it out a little, but keeping it effectively a spike. Then at the output, to keep it simple, let's say that. Now, since the system is linear, we could put in, say, half the spike and get half the output. Same shape, but half the amplitude. And now the trick. After a short delay, let's add a second spike, say 3/4 of the amplitude of the original spike, so that by itself it would generate this output. The two outputs overlap in part. We say they are superposed. Then, because the system is linear, the actual output is the superposition, which is the simple sum of the two constituent outputs.
That's it. The principle of superposition. Simple, but immensely powerful.
Powerful because any input waveform, however complicated, can be regarded as a succession of spikes, each generating its own output, each generating an appropriately scaled impulse response. Then, just as the input is the sum of the spikes, the output is the simple sum of all these constituent impulse responses.
The output at any one instant of time is the sum of a contribution from the impulse response at that instant of time, plus the contributions from the impulse responses at all past instants of time.
It is as though the impulse response is a memory, and the output now is a weighted sum of the input now and the input in the past. And of course, the longer the impulse response, the longer the memory.
This process of superposition is usually called convolution, the calculation of the output when we know the input and the impulse response. The distinction between convolution and superposition is just the manner of calculation. What we are really doing when we convolve an input with an impulse response is exactly what we see in this diagram: superposition. An input, an impulse response, and their convolution.
Let's get very, very comfortable with this, because we shall need it time and again. If the response of a system to one spike is like this, the impulse response, then the response to many spikes together is the sum of the individual responses, the overall output, the sum.
And the same is true when the spikes come so close together that they form a continuous waveform. Consider the case of a motorcyclist riding along the road. If the road is smooth, no problem. For the rider, the ride is good, level, flat. But if the road is bumpy, is there any way we can find out how the ride is now?
Of course, inject a spike and determine the impulse response. But how to...
On the smooth road, place one small stone.
Ah, yes. And there's the impulse response. The front suspension, a weight on a spring again, and the rear.
So now, for a given speed, we can calculate the movement of the rider on a bumpy road as the convolution of the waveform represented by the road and the waveform of the impulse response. In effect, we are viewing the road waveform as a succession of spikes generating an appropriately scaled impulse response for each one and adding them all together. Superposition, or what is the same thing, convolution.
So, as soon as we know the bike's impulse response, we don't actually need to ride it over different ground surfaces to know how well it rides. We can calculate it using convolution.
Provided there are no bumps big enough to make the springs hit the stops. That's right. And the same is true for any other linear system. Mechanical, musical, electronic. If we know what the system does to a spike, we can quickly and easily deduce what it will do to any other waveform.
At this stage, we can bring together everything in one diagram. In the time domain, we have an input waveform, which we convolve with the system's impulse response to obtain the output waveform. While in the frequency domain, the input waveform is represented as an input amplitude spectrum and an input phase spectrum. The input amplitude spectrum we multiply by the system's amplitude response to obtain the output amplitude spectrum. The input phase spectrum we add to the system's phase response to obtain the output phase spectrum.
And there is a Fourier transform relation between the input waveform and the input spectra, between the system's impulse response and the system's amplitude and phase responses, and between the output waveform and the output spectrum.
That then is the overall scheme connecting waveforms and systems. One simple, all-embracing, cohesive scheme. I like that.
So far, we know how to specify waveforms in both domains, how to recognize linear systems, how to specify such systems, again, in both domains, how to deduce the output in both domains, and how to move from one domain to the other using the concepts of Fourier. That's probably enough for part one, the first tape. In part two, we shall apply this knowledge to the improvement of signals, to hear the message better against a background of noise, to make an echo sharper or to make a picture clearer. We shall apply it to detecting influences that we thought we could not detect in sonar and in seismics, in medicine and in the market. And we shall learn how to do all this, if we choose, in the computer. So, see you in part two.